in this problem, it's a scenario that's really similar to what we did in lab when we took that metal washer and tried to determine the temperature of the flame by holding it in the flame and then putting the hot metal into a styrofoam cup of water. So I'm just breaking it down into two parts. So part one, you have to take the information about the metal and first figure out the specific heat. Okay, so you've got this metal object. It's in a beaker of hot water for sufficient time to reach thermal equilibrium. At that point, the temperature is 97.5 degrees. The metal is then lifted out of the hot water and placed into a styrofoam cup with this much water, where the initial temperature was this, and after the metal is placed in the water and it's allowed to, the heat is allowed to flow from the metal into the water, the water temperature rises to 27.6 degrees. So based on this information, you can determine the amount of heat that was absorbed by the water, right? Because again, you're thinking Q equals MC delta T. That relationship, that formula is always in the back of your mind. You know the mass of the water. Of course, you know the specific heat of water. And you know the delta T of the water. So that allows you to do a calculation of Q for heat energy absorbed by the water. And then you can take that and turn it around, and if the heat absorbed that much water, that means that the metal had to release that exact amount of heat. And knowing the mass of the metal and the delta T, so you know what the metal, you know the temperature that it started at, and the metal ended up at 27.6 degrees. You've got a delta T there, and so that's how we can get to the specific heat. So first, to kind of get everything organized, what I would, like I recommended here, is I would get a data table established. So you've got the metal and you've got the water. Okay, and so we need data for these, for both of these. So we're going to have mass. We've got specific heat. We have the initial temperature, we have the final temperature, and you've got the delta T. Okay, so it's going to be very straightforward. The metal is 46.04 grams. Specific heat, that's what we're trying to figure out. We don't know that yet. But the initial temperature of the metal was 97.5 degrees Celsius, right? And the final temperature ended up at the same temperature as the water in the cup. So the final temperature for the metal will be the same as the final temperature for the water. The delta T for the metal will be negative 69.9. Okay, it's negative because the temperature is going down for the metal. For the water, the delta T is a positive 6.1. And the mass of the water, it told us, was 115.21. We know the specific heat, 4.18 joules per gram Celsius. And the initial temperature of the water was 21.5. Okay, so now let me add a last column here. Let's calculate the heat. All right, so the heat that was released, or I'm sorry, absorbed by the water is MC times delta T. All right, so we just plug these numbers in now. Okay, 115.21, the specific heat of water, 4.18 joules, and the delta T for water was 6.1 degrees Celsius. And when you do that out, you should get 2,938 joules. All right. Okay, so we can put that in here. 2,938 joules. Now, if the water absorbed that much, we know that the metal released that much. So that would be a negative sign from the perspective of the metal, okay, because the metal lost that heat. It was exothermic for the metal, and so now we can, excuse me. Now we know, so we know that Q equals mc delta T, but this time we're trying to figure out what is the specific heat for the metal. So now we need to solve the equation for C, and when you do that, you should get Q over mass times delta T. All right, and now we just plug in the data for the metal. All right, so that's negative 29. I don't know why my marks keep disappearing like that. Okay, over the mass of the metal, 46.04 grams, and the delta T for the metal, as we said, was negative 69.9 degrees Celsius. Okay, and when you chug that out on your calculator, you should get 0.913 joules per gram degree Celsius. Okay, all right, so hopefully that'll be of help. Now let's scroll down, and for this I would recommend, again, let's go ahead and set up our table. So metal, water, so we're going to have mass, specific heat, initial temperature, final temperature, delta T, and we'll go ahead and put that heat column right up front. Okay, now let's fill in some data. The metal is the same as the previous problem, so it's still 46.04 grams. Now we know the specific heat, so we can put that right in, 913. The initial temperature, that's what we're trying to find out. That's what we're trying to find out. The final temperature is now 51.3, and that's the same for both the metal and the water. The delta T, for the metal we don't know, but we're going to be able to calculate that in a moment. The delta T for the water was 24.3 degrees. All right, so if you take 51.3 and subtract 27.0, that's positive 24.3. Backing up, the mass of the water is 114.82. Specific heat still 4.18, and the initial temperature of the water is listed as 27.0 degrees. Okay, so just as last time, we have enough data on the water to determine how much heat was absorbed, and so that's a good place to start. Let me just get a little more space here. So Q for the water is 114.82 grams times the specific heat of water times the delta T, which we said is 24.3. Okay. Just as an aside, I don't know about you, but it's just so nice to have your data organized. You know, especially in problems like these where you've got, there's a lot of numbers floating around. It's really good to have it organized so that when you need it down here in the calculations, you can just know exactly where to go. Okay, so this time the heat is a lot bigger, 11,663 joules. All right, so that goes here, 11,663. Therefore, that means that the metal released that amount of heat, and that's a negative sign. So now what we're going to do is, this time we know the specific heat, but we're looking for the delta T. Okay, so we're going to solve the delta T right now. And in your mind, you might be saying, well, wait a minute. What we're really after is the initial temperature of the metal, because if we know that, then we'll know how hot the oven was, where it came from. That's true, but don't forget, we're gonna, don't forget the relationship between delta T, T final, and T initial. We're about ready to calculate delta T, and we know from the problem, we know the final temperature. So once we get delta T, then it will be easy to calculate initial temperature. Okay? So, so we're calculating the delta T of the metal, and that's, when you solve for that, you should get Q over M times C. So Q is negative 11,663 joules over the mass, which is 46.04 grams, divided by the specific heat. And notice, I'm being really consistent about always including my units. All right, that's just something that you should definitely get used to doing. Okay, and so when you do that calculation, you should get 277.5 degrees Celsius, and that's the delta T. That's the delta T, not the actual temperature of the oven yet. Okay, so now we're ready for the grand finale, which is we're ready to solve for T initial. All right, when you do that, you'll find that T initial is equal to the final temperature plus the change in temperature, which is, final temperature was 51.3 degrees, plus the delta T, which is 277.5, and turns out that it's 328.8 degrees Celsius, which is pretty hot. How hot is it? Well, in order to get a little better feel for it, let's convert that to Fahrenheit. Fahrenheit is 1.8 times the temperature in Celsius plus 32 degrees Fahrenheit. And when you do that conversion, you should come up with 23.8 degrees Fahrenheit. Okay, thank you.